Well, thank you, David, for that very kind introduction. I never thought that when I was leaving physics as an undergraduate to go to graduate school in neuroscience that I'd come to the Kavli Institute for Theoretical Physics and be introduced by David Gross. And it just goes to show that when people think they're leaving physics, they're really taking it with them. And yes, right, you can't shake it off. But I really appreciate the kind introduction, and I also appreciate the KITP for hosting this workshop that we've run for the last 5 weeks, and halfway through the 5th week and now entering the 6th week. And it's been really exciting because it's been an opportunity for us to take theorists and people with primarily physics backgrounds and to bring them together with experimental biologists, people who are gathering cutting-edge data using modern methods in neuroscience to try to make some sense out of the nervous system in the way that a physicist might want. And it's been a real privilege to do it here. It's a beautiful and relaxing place to do it and a really good place to just think. And so, and in addition to that, I get to come and speak to all of you. So this is really a real treat. So thank you so much. So let's see. So as you've learned, I'm a neuroscientist by trade. I've turned my physics background into a career in neuroscience. I run a laboratory at Princeton University, and I've been there for the last 8 years, training students and teaching classes and doing research. But I'm not going to be telling you about any of that. I might tell you about a little tiny bit of that tonight. What I'm going to do tonight, I was going to do something entirely different. What I'm going to do is give you a sense of why you might care about neuroscience, why some of the beliefs that you may have about your own brains are not true. What I'd like to do is take some ideas that you have about your brains and bust those myths. I'd like to replace them with facts known from actual neuroscience research. And my ambition is to even let you walk out of here with some useful facts that you might use in your own lives when you walk out of here, when you're hanging around afterwards, just from day to day, things that I hope will help you use your brains just a little tiny bit better. So that's the goal. And my hope is to try to get through this in a reasonable amount of time so that I can entertain questions, because I've been giving talks since the book's been released about a month ago. And one thing I've noticed is that the questions are often the best part, because people often have very interesting questions about their own brains or about the brains of people close to them. And they usually have something good to say. Okay. So all right, so here's the subject here. This is the brain, and this is just a cartoon to illustrate to you the kinds of things that are packed in there and all these strange things in here. You can see a baby in a diaper and a clown and so on. And generally, what I'd like to do is introduce you to your own brains. Now, this book I wrote is, as David said, co-authored with Sandra Amit. Sandra is the editor of the world's leading journal of neuroscience, Nature Neuroscience. And, excuse me, I'm getting over a cold, and so I've got all kinds of paraphernalia here, which I need to get rid of. But Sandra is editor of the world's leading journal of neuroscience, Nature Neuroscience. And as I said, I'm a working neuroscientist. Now, one thing we've noticed is that when we go places, whether we're traveling to conferences or whether we just meet people like loved ones, or we go and talk to taxi drivers or art gallery owners or what have you, when we encounter people and we say that we work on the brain, in cases where people are interested in that fact, they will then start asking all kinds of interesting questions. And it'll turn into questions like, is it true that drinking kills brain cells? Is it true that playing Mozart to my baby will make her smarter? Is it true that we only use 10% of our brains? And these are the kinds of questions that I think some of you have perhaps thought of at one point or another in your lives. And you may think in your everyday lives that the answer to those questions is yes. It turns out that the answer to all three of those questions I just posed to you is no. And those are examples of myths, that beliefs that we hold dear about our brains that we don't even realize that we have, but permeate our culture and are very much false. So what I'd like to do is use that as one starting point. And I also want to sell you on the idea of neuroscience. And since you came out tonight on this beautiful evening, I don't need to sell it too hard. But I just want to point out to you that neuroscience really does permeate the culture. And this is just to give you a few examples of it. I think I mentioned to you the idea that Mozart can make a baby smarter. And this is exemplified in this product, Baby Einstein, which is a product that's used to help babies become smarter. Here's the great boxer Muhammad Ali, and here he is in his prime, and here he is with Michael J. Fox, and I think many of you already know that these two are sufferers of Parkinson's disease, and so that's one way in which we hear about neurological ailments. Here in popular entertainment, we have a couple of examples. One is the movie Memento, which is about someone with a very particular kind of brain damage that turns out to be very accurately portrayed in this movie. And finally, we have this example here, and I think depending on your point of view in the audience, some of you will immediately focus on this guy. Okay, this is John Nash, my colleague at Princeton. John is a great mathematician and also is a schizophrenic in remission. And then this is a movie that the story of his life got turned into featuring this guy here. Okay, so, and I'm guessing some of you recognize him as well. All right, so to turn this into something having to do with our daily lives and the lives of those close to us, here's just some simple pie charts to just show you the kind of impact that neurological disorders and psychiatric disorders have on our lives. Just to walk you through it, this is all referred to the United States population. In the United States population, there's a wide prevalence of neurological disorders, as is the case in all populations. That includes stroke, which afflicts several million people in the U.S., epilepsy, Alzheimer's disease, as well as other diseases such as Parkinson's, which I mentioned before, Huntington's disease, developmental disorders, which includes mental retardation, cerebral palsy, and in the last few years, there's been a lot of public attention paid to autism, and so that falls into the general category of developmental disorders. And in fact, it's appreciated that this slice of the pie is somewhat larger than previously thought. And if we think of psychiatric disorders, these are also disorders of the brain, and these affect about 1/5 of the U.S. population. And these include schizophrenia, depression, anxiety disorder, and alcohol and drug abuse. And you can see here, if you can read the numbers here, this adds up to about 40 million. Okay, so it's really quite a large part of the U.S. population. So these are, actually at this point, this is an old chart. It's now up to about 50 million, okay, because the United States population has increased. So these are reasons why you should care about neuroscience. Now, what I want to do with you, what I want to do for you tonight is to tell you ideas about the brain. And I'm going to separate them into certain categories. Okay, as I said, the categories are beliefs that you may have which are false, and when you see a false belief, you will see this mythical creature. Okay, if I give you something that's true that might be interesting, then I'll give you this, which depicts you telling a friend about it later, and I'll give you some useful tips. Okay, so that's the way we're going to set it up. Okay, so just to show you the kind of thing that shows up in the culture, I just want to show you an example. This is from a defunct newspaper, but some of you may know it. Okay. It's the Weekly World News. And I'll read you the headline, especially, are we broadcasting to the other room? Okay, so maybe they'll need a little help. Kaboom. Chess player's head explodes during championship match. Okay, and so here's a depiction of a chess player who for some reason is wearing capri pants. But anyway, this chess player's head has undergone an unfortunate transformation. And it says here, although hypercerebral electrosis is very rare, it can kill. All right. So this may be a piece of neurological information that you don't know about. It turns out that the reason you don't know about it is it doesn't actually exist. Here's an example of another headline from this fine publication: metal eyeball found at UFO landing site. Okay. So these are examples of, okay, this is an idea that is not true. All right. And I'm going to make a serious point about what it is that makes this statement not true. And the reason it's not true is that your brain uses a very small amount of energy, a really amazingly small amount of energy. Measured in the same units of power that we use to operate our appliances, the amount of power used by the human brain is about 12 watts. And that 12 watts is about 1/6 of the energy used by the entire human body. And so this is, in some sense, the basic reason why that idea is false. It's that the brain is an amazingly efficient device. If you think about how that compares with supercomputers, per calculation, if we knew what a calculation in the brain were, per calculation, it would be likely to be an extremely efficient calculation. To just give you an example of what I mean, just to familiarize you with the brain itself, it's about 3-pound object. It's got about 100 billion neurons. And on average, these neurons these brain cells make about 10,000 connections with other neurons. And that means in total, there's something like 10 to the 15th synapses in the brain. Okay, so this is a tremendous number of connections, an unimaginable number of connections, at least for someone who left physics long ago. And as I said, its usage is 12 watts. And just for comparison, if there's something that uses approximately that much power, the light in a typical refrigerator uses 15 to 40 watts of power. And so in some sense, we do not compare very favorably even with the dimmest of bulbs. Okay, and so. But I'd like to think that, I think we'd all like to think that we do more with our brains than the light in the refrigerator. Okay, so that's a true fact, I guess, as opposed to a false fact. But anyway, that's a fact about the brain. I should also say that about 1/6 of the body's energy budget goes to running the brain. In children, it's quite large. It's more like half of the total energy budget of a child. goes to running the kid's brain. Okay, so that's an amazing amount of energy being used here, right? So it's quite a remarkable thing. So speaking of children, I want to start, I'm going to walk you through a few myths. I'm going to do it approximately in the order in which we encounter them in life. So as I mentioned to you, there's this product, Baby Einstein. I don't want to pick on Baby Einstein. It's an example of a whole genre of videos called baby DVDs. And these all take advantage of the fact that we believe that somehow playing classical music will make babies smarter. And of course, there's this child prodigy, Wolfgang Amadeus Mozart. So he's sort of a poster child for this kind of idea. And you won't be surprised to hear that this idea is false. So I want to unpack this for you a little tiny bit. This idea came from a study that appeared in a regular peer-reviewed scientific journal and then got mutated basically out of recognition. So the original study that led to the idea that somehow Mozart was good for babies happened about 15 years ago. It was a study in which a group of subjects were given aptitude tests to take. And they took these aptitude tests before or either without or after being played about 20 minutes of classical music. And it was observed that after listening to the classical music, the subjects did better on this exam. Okay. Now, that result got reported to a moderate extent in the press, but then it died out. It became less interesting. But then there was a book that came out called The Mozart Effect. And The Mozart Effect was sort of a mystical book that purported that, in fact, this effect was true also for infants, and that if you played the music to babies, it would make them smarter as well. Now, I want to tell you a few things about this study that make it a little bit hard to interpret in that light. One fact is that the original study was done on college students, not on babies. Another problem with the original study was that the effect was only on 1 out of about 6 aptitude tests. The effect only lasted for about 20 minutes. Okay, so it's not a long-term effect. And worse yet, for fans of peer-reviewed science, it was not reproducible. So people attempted to reproduce it, and it could never be reproduced. Okay. But to put it colloquially, it's too late. The horse is out of the barn. Okay, so what happens in many cases of brain myths is that there's some idea that people have because they read a news story, and it's exciting, right? Because you read something in the paper and you say, holy cow, this is really great. Playing Mozart is good for babies. Vioxx is good for me. There's all kinds of things that one hears about that come up in the papers. And so our imaginations run away with this. Meanwhile, the scientists go off to the lab and do their thing and say, well, we're going to go do these experiments and we're going to follow up on this. And the scientists are doing something, and no one's paying attention to the scientists at this point, right? They're off doing their geeky science thing. And so, of course, it's too late by that point. So it turns out that this belief, as appealing as it may be, has no scientific factual basis. And in fact, there's a problem. And given what's known about brain processing, babies are not really equipped to appreciate classical music. They have to learn a lot of tonal relationships and so on in order to appreciate it. And this is a somewhat, to my eye, as the father of a 10-month-old baby, I find this somewhat disturbing. And there was, in fact, a study that came out last year. And there's a study by researchers in Seattle in which they found that babies who watched an hour or more a day of these baby DVDs had vocabulary acquisition that appeared to be slower than babies who watched Sesame Street, other children's television, grown-up television. Okay, and so they, in fact, had slightly slower vocabulary acquisition. Now, I shouldn't scare you too much. This is not necessarily the case that those kids grow up to have poorer vocabularies, because there's a question of what they end up with. But the observation appears to be that there's something about this that's not favorable for vocabulary acquisition. Now, this shouldn't be too surprising, because if you park your baby in front of a television for an hour a day, then that might not necessarily be good for vocabulary. The same study had another result that hasn't been talked about in the press. So this attracted a lot of press. The same study also showed that something that led to a slight increase in the rate of vocabulary acquisition was being read to by a parent for an hour a day. Okay. Now, if you think about it, this is not such a surprising myth to debunk, but I just wanted to leave you with that idea. Okay, and so just to talk about infant development a little tiny bit, there's a huge amount of change that's happening in infant brains. As I mentioned to you before, children and infants spend something like half of their body's energy budget running their brains. And part of the reason for this is that there's a tremendous rate of growth in the brain in infants and children. There's formation of many, many brain cells. And in fact, something like 10 times as many brain cells are produced in infant development and prenatal development as ultimately survive to adulthood. So to repeat that, 90% of the brain cells born in a baby's brain do not make it to adulthood. So there's some pruning back process in which there's this massive outgrowth and then a loss of connections and a loss of nerve cells leading to the brains that we possess as adults. And I just want to put it out there, but also point out that, in fact, this is a mystery to neuroscientists. It's not understood why this is the case, why you would need to put up this massive number of cells in the brain and then prune it back. It's almost as if some kind of scaffolding were being put up and some kind of construction project were going on, and then things get taken out and then tossed out, and then what gets left is the brains that we have as adults. And so there's this huge period of development and also sensitivity to experience that happens early in development. And this is just a picture to help you remember that fact. Okay, so now I want to skip to a later stage in life, and a stage in which you exercise upside down. But a stage in life that occurs surprisingly early. So mental functions increase as we develop and grow and mature. But as it turns out, some of those functions decline starting at a surprisingly early age. So to give you an example, memory, right? So the kind of short-term memory that, say, help you remember where your car keys are, peaks by the age of 30. And the implication of that facility peaking by the age of 30 is that after the age of 30, it starts to decline. And so starting at the age of 30, at least one brain function begins to decline slowly, but steadily throughout life. And there are other functions that decline later in life. For instance, we all are aware of people who start to be a little bit slower as they get older, or maybe are less good at planning for the future, or less good at really focusing on tasks, that kind of thing. And this is an area of obvious concern, right? Because we all go through this process, and it's something that we're concerned about. And something has come up in response to this, and it's a whole industry and a whole popular belief that we can do brain exercises that can help our brains stay young, right? So I'm curious, actually, how many people in this audience do Sudoku puzzles? And how many of you do them because you think that it'll help your brain stay young? Right? I mean, it's right. I mean, they're enjoyable to do, right? I mean, I love doing Sudoku puzzles, but there's this idea that somehow they can help our brains stay young. There's a huge industry of this kind of thing. Sudoku puzzles obviously don't cost a lot, right? You can just rip them out of the paper, or you can take them out of the in-flight magazine or what have you. But there's an industry of brain exercise software that's aimed at people to help them keep their brains young. And the dirty little secret of these brain exercises is that they don't do all that much. Okay? The effects that they have on long-term brain function are small. They're measurable. They can be measured. But they are small, and they typically are restricted to the type of tasks that perform. So, for instance, getting better at Sudoku puzzles makes you better at the kind of things you do in Sudoku puzzles, whether it be spatial reasoning or grouping, that kind of thing. So you get slightly better at those things. The only, of these tasks, the only thing that really gets better by a lot is reaction time. But the typical effect is, for those of you who are statistically minded, is about 0.2 standard deviation. And if you're not statistically minded, that means that if you're at number 10 out of a group of 20, so if you're in the middle of the pack, then that is enough to get you up to about number 8 out of 20. Okay, so this is in one area of brain function. So you can see that there is an improvement, but it's not a huge improvement. It turns out that there is something else that you can do, and you can see that the answer is right here. The answer is that the thing that you can do to help maintain brain function later in life is physical exercise. It's been demonstrated that physical exercise, for instance, of a form such as fitness training, where you get on the treadmill, get on it right side up, and get your heart rate going, and do this, say, 3 times a week, for 20 minutes, that kind of training will increase function across the board, especially in categories of function that people who are getting older are concerned about, such as executive function, by 2/3 of a standard deviation. So first I'll tell you what executive function is. Executive function involves planning for the future, self-control, making plans, executing those plans. Also things like working memory. Okay, so for instance, things like maintaining a phone number in your head while you go dial the number, that kind of thing. These are functions that begin to decline in the 70s and 80s in most people. And it turns out that decline can be slowed or prevented in people who undertake an exercise program of fitness training. And so physical exercise, not Sudoku, will keep your mind alive. So that's a major lesson from neuroscience for how one can maintain brain function. Now, the other major predictor of maintained brain function later in life is an intellectually engaged lifestyle. And this doesn't mean just doing Sudoku puzzles, although you can imagine that Sudoku could be part of it. It also involves other complex activities. It could involve playing bridge. It can involve learning a language, travel, having other kinds of complex hobbies. Many people who work with their brains for a living automatically have an intellectually engaged lifestyle, so many professionals don't have this problem too much. And it's been observed experimentally in studies that the number one correlate of maintained brain function late in life is level of education. And from my understanding of the Friends of KITP, this is a group that has lots and lots of education. And so you should feel good about that and then go to the gym. So that, okay. Now, here's another editorial we had, and I should say, by the way, these editorials are really good for getting people interested in the book. It's better than sliced bread. So this one is currently, well, I'll get into this. This is a great editorial for us from a purely book-oriented standpoint, because it turns out to be the most emailed story it was the most emailed story of the week. It's number 2 most emailed story of the last month. And it speaks well for our country that there is one story ahead of it, and it's Barack Obama's speech on race, which in our view is more important than, well, I'll tell you this and you can tell me what you think, which you think is more important. So I told you that something like Sudoku can help exercise and improve one particular area of brain function. Surprisingly, there is one type of brain function that can be improved by exercising it, and it's like a Sudoku puzzle in a sense, and it's willpower. It turns out that the mental facility of willpower is a specific capacity that our brains generate. And it turns out that this capacity has several properties that you might expect of a particular facility. And it's in some sense like a muscle. And it's like a muscle in the sense that you can wear it out. So if you get tired, you can exhaust your supply of willpower. And you can also exercise it like a muscle. So I'll give you an example of what you can do to deplete your willpower. Studies by the psychologist Roy Baumeister have shown that you can do something like you can give a group of subjects radishes to eat, okay? And if you give them radishes to eat, then they will spend less time working on a very hard puzzle that you give them right after giving them the radishes. Now, I should interject that the premise of this is that on average, people don't like radishes. And so there may be a few of you who really like radishes. Okay, so this is not really for you. This is an average across a group. And this study is made more intense by the fact that these radish-eating students were presented with the radishes in the presence of other students who were given freshly baked chocolate chip cookies and consumed in front of the students with the radishes. Okay, so it's a real torture game. But that's just one example. And so if it were just that one experiment, it might be just a silly experiment. But it turns out that this has been repeated over and over with many permutations. Another permutation is, say, negotiating a difficult social situation and combining that with a task where you have to circle all the E's on a piece of paper, on a piece of text. Okay, so these are really very different tasks. And so to give you an example, circling all the E's on a piece of paper depletes you of some resource that you would use to watch a very boring video of a table and a wall in which nothing ever happens. So people spend less time watching the boring video after they have had to circle E's for a while, right? So despite the silliness of these tasks, they all converge on a common result, which is that willpower appears to be some common resource in our brains and that we can wear it out. Now, the good news is that willpower can also be exercised. Okay, so for instance, you can train your willpower. So to give you examples of willpower training, people who undertake an exercise program for several months are found later to be better able to stick to a diet, are better able to control themselves in social situations. It's really quite a remarkable thing, but there appears to be some physical resource in the brain that's willpower. And I should say that it's not known what this resource is. It's not known where it is. There is some speculation that it's in a part of the brain called the orbitofrontal cortex, but it's really not known exactly where this resource is in the brain. And so this is an area that at a psychological level is well defined, but in terms of the neuroscience is very much an open question. And this is an example of where, if we look at the other end of neuroscience from physics and from cellular physiology, if we start thinking about cognitive phenomena that make us unique in the world, there's a whole other category of phenomena that's at the other end of neuroscience that's sort of up there with psychology at that end. And so you can see that neuroscience is, in fact, a very broad area of research. Okay, 8:35. Okay, so just to, again, leave you with an image. The image is this factual idea that, in fact, one can exercise brain capacities in a specific sort of way, but not necessarily in the general way that's presented to you in the culture. And just to give you an idea of the kinds of things that are possible in the brain, this is a picture of my colleague at Princeton, Professor Elizabeth Gould. And Liz's lab, in conjunction with Charlie Gross's lab, also at Princeton, have been very interested in a recent finding that Liz pioneered, and that's that in addition to activity and practice changing the brain's function, there are structural changes in the brain. And if you think about that, that has to be the case, right? If experience changes the brain, or if when you learn something it stays in your head, there have to be changes that happen in your brain. And this is a whole area of neuroscience that's attracted a lot of interest in the last 50 years. And for instance, Eric Kandel was given the Nobel Prize in part for his contributions to the understanding of neural plasticity. Liz's contribution is extremely interesting, and it speaks to another myth that we hold in the culture, and that's that once we reach about the age of 6, it used to be believed that we stopped making new brain cells. It was believed that we made all the cells we were going to make by the age of 6, and after that we only had neurons die. What Liz and Bruce McEwen and Charlie Gross and a number of others have found is that, in fact, the brain makes new brain cells throughout life. Okay, now different brain regions make it at different rates, and so some brain regions make new cells at a fairly fast rate. Those include the olfactory bulb, which processes smells, and the hippocampus, which is important for spatial memory and certain types of memory involving navigation and remembering facts and places. And so those brain regions seem to generate new cells at a reasonably high clip. Other regions of the brain, such as the cortex, which is most of our brains, right, the 3/4 of our brain, that's this folded part that we all know from photographs on science shows, the cortex generates new cells at a very slow rate, so slow that, in fact, some laboratories cannot measure it, and so the phenomenon itself is a little bit controversial at present. But you can see why this is very interesting, right, because now this, again, this is interesting at two levels. It's interesting because at the level of basic science, it breaks an old idea that goes all the way back to the origins of neuroscience, that adult brains don't make new cells. And it also opens up the possibility that at some distant point in the future, one might be able to understand this process of generating new brain cells well enough to help regeneration in brains that are damaged or that are senescent. Okay, and so this, at some long distant future horizon, may become extremely useful for everyday life. Okay, now I want to, I think I'm getting close to the end here, and then I'll be glad to take questions, but I want to leave you with one of the oldest myths of all. And I think with an audience like this, I don't really need to tell you that the myth itself is not true, but I just want to tell you who this guy is. This is William James. And William James is considered the founder of, one of the founders of modern psychology, and he's also considered a foundational figure in neuroscience. And he was a popular intellectual and made speeches and gave lectures and so on. And he said, we are making use of only a small part of our possible mental and physical resources. And he said this exactly 100 years ago. And this idea was true, but somewhere along the way it got turned into another idea. And it got turned into another idea by this guy who is not a neuroscientist, but was a very inspiring speaker, Dale Carnegie. And he was basically able to win friends and influence book sales by saying, you only use 10% of your brain. All right? And so this is the earliest that people have been able to trace this idea. It turns out that someone a fellow named Lovell Thomas, who wrote the preface to this book, cited this fact. And Carnegie used to go give lectures and say, you only use 10% of your brain. It is known from the writings of William James. And so he cited William James, who didn't say anything of the kind. But this is an interesting myth because it speaks to our desire to improve ourselves, right? Because the idea is, wow, we only use 10% of our brains. You know, Einstein probably used 12% of his brain. And if I could only squeeze out a couple more percent, maybe I could discover quantum chromodynamics or something, you know. And so it turns out that there are things that you can do to improve your brain function, but this is not the right way to think about it. And so this is interesting. It's also a very widespread belief. In fact, one of the attendees at this conference, where is she? Is Susanna in this room? Yes. Susanna Herculano Huzel, who's visiting from Brazil, is in the very back of the room. She's conducted a survey in her native country, Brazil, showing that the majority of people in Brazil believe this fact. Okay, and so this is, in fact, a worldwide myth. And now I want to just close with a little tiny bit of science. And I'm actually going to give you one brain trick before I close. And this is just to bring you back to the present of neuroscience research. The present of neuroscience research is that it now becomes possible to quantify exactly what parts of the brain are active, how much of the brain is active. And this is due to the development of physical techniques for investigating brain function. And these techniques, as it turns out, are developed by physicists. My mentor at Bell Labs, and who is now a colleague of mine at Princeton, who came there a year after me, David Tank, has made fundamental contributions that are in use in laboratories around the world. One is functional MRI. Okay, so this is using magnetic resonance imaging to image brain function, and it's a physical effect also called the Bold effect. And another kind of technique that's used is a kind of laser microscopy that allows laser light to be used to observe activity in neural tissue at a depth of less than a millimeter, which is not all that much, but it becomes possible to observe brain tissue in its natural habitat doing thinking-like activities. And so these are technologies that are made possible by physicists working with biologists together to make progress in developing better probes for brain function. So this is just an example of how physics and neuroscience can come together. Okay, and so I was going to show you a movie of that, but instead what I'm going to do is I've given you very high-level things, and I'm going to close with this last thing, and then I'll take some questions. This diagram depicts a myth about cell phone use. Now, I think many of you have cell phones. You certainly have landlines, and it's true for cell phones and landlines. If you're trying to hear in a crowded room, you probably, I'm guessing, where do you put your hand? You put it here, right? This is what you do to try to hear better. So you may have discovered that this does not work very well in helping to hear in a crowded place. So that has to do with the fact that phones use a technique called full duplex. This is what engineers call it, in which sound gets transmitted from your voice and also from the room noise into the mouthpiece and then into the earpiece to give you a more natural feeling. And now what you're doing here is you've created a situation in which you're trying to distinguish your friend's voice mixed in with the sound of the room around you, and then you've got the room around you in the other ear, and now you've got room noise coming into both ears. Okay? And this is a very hard circumstance for your brain to decipher. It's a very difficult situation. So it turns out that a better thing to do is to do what this woman on the left is doing, is to put your hand over the mouthpiece. Okay, so if you put your hand over the mouthpiece, now what you're doing is you're breaking that full duplex mode. And you're creating a situation in which you've got your friend's voice in the left ear, you've got the room noise in your right ear, and this is something that your brain is very well wired to do. Your brain is very good at source separation when the sources are well separated like that from the left ear and the right ear. And so if you do this when talking on the phone, people will look at you and think you're odd, but you'll be the smart guy or the smart gal because you will know that you'll be getting better use out of your cell phones, okay, or your landlines, as I said. So I encourage you to all try this out at some point in the next day or so and let me know, because it works for most people. So this is a practical trick based on how the midbrain processes sounds that can help you use your brain just a little tiny bit better. Okay, so that's the useful tip. And of course, there is the inevitable self-promotion. This is the book, and so I encourage you to at least consider looking at it. And as you can see, if your chosen language is not English, it's coming out in a number of other languages, including German, Chinese, Spanish, and there are 18 translations worldwide. And so whatever language you might like, including Albanian, is available. So why don't I leave it at that and take some questions? Oh, should I show? So our director wants to see the movie, so why don't I just show that real quick, and then we'll go ahead and go to, see, I have to find the movie. Okay, so this is a movie using two-photon microscopy, and this is just to give you an example. Maybe we need the lights down just for a second here. This is a movie showing what kind of thing is possible with the new technology, and this is done using two-photon microscopy, the laser microscopy that I described. And basically what this is a means of observing brain activity in a behaving animal. And this movie is going to directly refute for you the 10% myth. And basically what we're looking at here is we're looking at a part of a mouse's brain, and it's about 150 microns wide, so that's 0.15 millimeter. And it's loaded with fluorescent dye, and you can see each of these things here is a brain cell. Okay, so you can see there's about 30 brain cells in this field of view, maybe 20, right? And it's loaded with a fluorescent dye, and this fluorescent dye changes brightness when the neuron is active. Right? And these are data taken, there are two labs that do this kind of work at Princeton. One is my own laboratory, and this is done in the laboratory of David Tank, who's one building over. And this is now the brain of a running mouse. Okay, so this is a mouse that's running in place on a ball, and that green bar is its running speed. And each of these red flashes with occasional blue flashes that are going by, can you see the little red flashes? They go by occasionally. They're a little hard to see, but you can see those. Okay, each of those flashes is a brain cell firing. And so this neuronal firing, you can see, happens sometimes in nearly all the cells at once. And basically, it's not really possible to find very many cells that are not active. And so this is just a demonstration to show you the kinds of things that are possible with the new technologies that are being developed now at universities and laboratories around the country and around the world. The idea here is that it becomes possible to spy on these circuits, right, in action. And so it becomes possible to determine, in a very real sense, what brains are doing when they're thinking. And so this is very exciting to me because this is where I think neuroscience is headed in the next 10 years. Perhaps to your eye, this movie may look a little bit muddy, and that's part of the problem. We're now developing technologies to make these images sharper using molecular biology. And I won't get into too much detail, but the idea is that one can do these things with protein engineering, transgenic animals, and so on. And I think you actually may have seen this movie before. So, all right. So anyway, so that's science land. All right. So anyway, so.
Okay. Well.
Oh, is there? Oh, do we?
Before we start our music, probably an unusually long round of questions. Given the subject and the proclivities of the speaker, I want to remind you all that once we run out of questions, we will have refreshments in the courtyard, in the common room in the courtyard, to which you're all, as usual, invited. And in addition, there's a signing, right?
Yes.
You're going to sign whoever has a book or has bought a book. Not any book, that book.
I'll sign other books. But,
oh, okay.
But
so we have people with microphones, and I'm sure there are lots and lots of questions. So we could start.
Okay.
Thank you very much. I would appreciate your clarifying your comments about the reserve of willpower, because as I understood it, there was a bit of a conflict, so I'm confused. On the one hand, you said that if you exercise your willpower, you kind of use up some reservoir of it. On the other hand, you said it's like a muscle, it can be strengthened. So if you could clarify that, I'd appreciate it. And then I'm also very interested if you can say more about children using 50% of their total energy on the brain. Are they using it to work it, or is that the process of growing and pruning and developing it, if that's known?
Right. So these are great questions. Let's see. So the first question is an apparent contradiction with what I said about willpower. Exercising the willpower and testing its limits can change the size of that limit. Okay, and so the idea here is it's the same principle as neuroplasticity that's been observed in many neural systems. The idea is that you can change how much that limit is by exercising it. So for instance, I'll give you examples of activities that are sort of in this category. One example is military boot camp. Okay, so boot camp is meant to build character. There are many things that we do, for instance, in urban outreach programs to help people lift themselves up by their bootstraps. You have kids who are taught citizenship. This is almost certainly some kind of willpower training. Okay, another example of willpower training, for those of you who remember the Watergate era, G. Gordon Liddy, right, put his hand over a flame until it blistered his skin. If you've seen All the President's Men, that's where I know this from. And someone asked him, well, what's the trick? And he says, the trick is not minding. Okay? And so now look, the guy's a maniac, but the thing is, he knew something there, and the something he knew was that there's effortful will, what psychologists call, when you run out of it, it's something that psychologists give the technical name of ego depletion. Okay, and so which is a great name, ego depletion. And so the general idea is that there are certain kinds of effortful attention to tasks that runs out. And so my point was that it runs out, but you can extend how large it is. Okay, it's just in the same way that when you can wear out the amount of reserve that you have, say, for exercising your muscle through whatever process that is, lactic acid accumulation or what have you, but you can increase the limit. Okay, so that was the idea. And as far as the energy use in children's brains, yeah, that's a really interesting one. A lot of that is almost certainly just operating the brain, the kid's brain from moment to moment. This is a finding that's buried in the scientific literature from about 40 years ago. I found it in the library while trying to get at the 12-watt idea. I was trying to track that down. And I discovered this 50% figure. It's phenomenal. It's not remarked upon in the literature at all. Scientists have not spent a lot of time talking about it in the last 10 years or so, in the last 20 years or so. But it's a finding that's in there, and it's an amazing finding. And I don't really have a whole lot to say about that, except that it probably involves a lot of moment-to-moment operation. Let's see. I guess, David, are you choosing people to ask questions? Because you have to. Okay, so in that case, I'm going to stop pretending to call on people.
At the other end of things, do you have any clues or ideas about Alzheimer's?
Certainly, Alzheimer's is a very well-studied subject area. It's a major emphasis area at NIH. Let's see. So, at what level do you want me to answer this? So I'll give you. Okay, so Alzheimer's is an abnormal loss of mental capacity that develops, and it's separate from the normal declines that happen with aging. And so often people experience some decline in mental capacity over time, and that is actually not a good predictor of Alzheimer's disease. And so the rule of thumb is that you have certain kinds of memories that you lose, like the name of a person that you met recently, or perhaps even the name of a person that you've known for some time. And these things are natural examples of decline. A good rule of thumb would be, if you can't remember where your glasses are, then that's normal decline of function. If you forget the fact that you wear glasses, then that's much more worrisome, and that's something that's more deeply held knowledge that you've had years to transfer from one part of your brain to another part. And it's roughly speaking, something that's transferred into deeper memory in a sense. Your brain has something like half a dozen different memory systems, and that kind of loss is a more serious thing. There are treatments for Alzheimer's that are, there's no cure for Alzheimer's, but there are treatments that can be given. There have been some experimental drugs that have been approved that can help to some degree with mental function, although one benchmark drug for a really good cognitive enhancer would be caffeine or nicotine. These are very good drugs for cognitive enhancement, and the drugs that have been developed are not nearly so good as caffeine or nicotine. Okay, it's funny, caffeine, nicotine, if it were discovered today, would be a wonder drug. Right? Just because nicotine is a cognitive enhancer. You smoke a cigarette, there's these receptors in your brain that mediate attention and are thought to mediate alertness and so on. They're called acetylcholine receptors. They come in multiple flavors, and one of the receptors is called the nicotinic acetylcholine receptor. And so nicotine directly activates those structures in the brain. And the things I said before about exercise is something that can reduce the likelihood of onset of Alzheimer's disease. Other things, there's a general rule of thumb, which is that things that are good for your heart are also good for your brain. And so, for instance, red wine is also good for reducing the risk of Alzheimer's disease. So.
Okay. Shall I go ahead? Okay.
Oh, wait.
I've got the microphone.
So despite the fact he didn't have the limit is up to 3 glasses of red wine a day for men, 2 for women.
Okay. Actually, you've gotten into my next question already. We all know that certain drugs can enhance athletic performance for bicycle racers or other athletes. So there are probably chemicals that can improve the brain function as well. And you've already started to talk about those, so maybe you could say a little more about that.
Yeah, so let's see. So one category is these drugs that are used for treating people with Alzheimer's-based dementia. One such drug goes by the commercial name Aricept. It's also turns out to be used for other kinds of dementia, such as stroke-related dementia. Its effects are modest. They're noticeable, but they're not large. Another kind of whole category of drugs is a category of drugs called nootropic drugs. And I don't know anything about the origin of the word nootropic, except there's an umlaut over the second O in nootropic. But that's a whole category of drugs that are being developed for enhancing mental function. Again, those effects are modest. And I'll go back to what I said before, which is remarkable drugs for enhancing mental function are caffeine and nicotine. And these other drugs have a large hill to climb before they can be as good as those 2 drugs.
In meditating, you try to not be thinking. I was wondering if some other part of the brain starts acting up, or do you have any traces of anything at all, or is that a false concept?
So the short answer to this question is that there are multiple kinds of meditation, and getting into the subject of meditation involves learning about the taxonomy of meditation. But roughly speaking, in cases where people have looked at it carefully, meditation affects brain function. Okay, and there are multiple ways in which this is observed. Just over dinner, we were talking about how, for instance, the kind of quiet, peaceful meditation leads to increases in a certain high-frequency oscillation in the brain called the gamma band, and this is a high-frequency oscillation. Another example is that there's a guru who claims to not feel pain. He claims to not feel a needle being pushed through his cheek when he's in a meditative state, and he was put in a brain scanner, and the part of his brain that normally would report this painful sensation didn't light up at all. Okay, so that's a physical piece of evidence that there's a direct neural correlate. In some sense, that's not surprising, because if he's being honest and saying he doesn't report the pain, then there must be something happening in his brain that reflects that. But it is remarkable that it is possible to measure such a thing. Other examples of meditation are it's possible to monitor changes in brain function, and for instance, in Carmelite nuns when they experience mystical union with God. Okay, and so all these things are things that can be measured. And so just the general answer to your question is that meditation does real things to the brain, and they're measurable. It doesn't necessarily lead us to understand those states any better, but it is interesting that one can measure those phenomena.
Go ahead.
Is there any evidence that diet influences the brain significantly other than chocolate brownies? Particularly, the effect of malnutrition on mothers and their offspring.
That's a great question. People are often very interested in nutrition and diet on the effects on brain function, and people get really interested in omega-3 fatty acids and all these other things, and ginkgo biloba. Generally speaking, those are not very large effects. The time when brains are most sensitive to deprivation or other kinds of dietary influences are during pregnancy and early development. And so, for instance, I'll give you an example of this. Since World War II, in many industrialized countries, IQ scores have gone up by an average of about, I think, 3 points a decade. Okay, and so this is in school children, and this is really remarkable because it's much faster than biological evolution in the sense of genetic change could possibly work. And what's believed to be the case is that what's happening, if one looks at the statistics carefully, is it appears that the bottom half of the population of, say, school kids, for instance, in one study in Spain, the bottom half of the population seems to be doing better. And the likelihood is that this has to do with removal of deprivation from the environment. Okay, so that's one part of the answer. Now, for those of us who are already done developing, the answer to the question about diet is that, I'll go back to it, it's things that are good for your heart are good for your brain. And so many aspects of this are kind of dreary. Green leafy vegetables, not too much saturated fat. It's okay to have some dark chocolate, especially if you have high blood pressure. Dark chocolate helps with that and reduces the risk of stroke. And a little bit of red wine. And so basically things you do to take care of your heart will also take care of your brain. I would not bother with ginkgo biloba. There's no convincing evidence that that does. There's no good peer-reviewed evidence for that. So, yeah, take care of your heart.
Professor, in patients who have suffered from the severe psychological trauma that leads to conditions such as post-traumatic stress disorder, or people who have severe, long-lasting chronic pain, is there any understanding in at the biochemical level or neurochemical level as to what the cause is of the widespread disruptions in normal brain function and the psychological and behavioral consequences that come therefrom?
Yes, these things are understood, and I could give a long-winded answer, but I'll just give it like this. Post-traumatic stress disorder is real, and we know it's real because it's described in literature all the way back to the Odyssey, to the Iliad. So, for instance, Achilles had post-traumatic stress disorder. He reported in that poem he'd come back from war and was unable to live normal life, and so that's an example of how far back the description of that goes. Post-traumatic stress disorder is thought to involve changes to fairly deep brain structures that are mediated, among other regions, by, for instance, the amygdala, which is important for processing intensely fearful stimuli. And many of these brain regions participate in a kind of learning called fear conditioning that is a type of learning that can happen in one trial. Okay, so for instance, another kind of learning is like learning a dance step, takes hundreds of tries for most people to get better at, but fear conditioning can happen in a single trial. And so there are treatments for this that involve pairing the fearful stimulus, the fear-inducing stimulus, with innocuous stimuli that then eventually persuade you, after many, many trials, that the original stimulus is not dangerous. And so it's deep brain structures that are involved in processing fearful information that are involved in PTSD. What was the other disorder you wanted to know about?
Related to people with chronic painful conditions where their lives are disrupted by an extension of whatever the pain stimuli is in the brain.
So pain's a really hard subject to study because pain appears to be entirely mediated by central mechanisms, which means that it's literally in your head and that it's not so strongly correlated with the physical sensation. And an everyday example is that I've got this baby. She hits herself on the head by falling down, and I've discovered that I can persuade her that it doesn't hurt by picking her up and saying, yeah, and playing with her, and then she forgets that it hurts. Okay, and so that's just an example that for some reason comes to mind and as it turns out, chronic pain is a very hard problem to address, but it's one of the very few neurological issues that appears to be well treatable by acupuncture. In most cases, acupuncture does not have good support in peer-reviewed literature, I mean, it doesn't say that it doesn't work in many things, but the one case in which peer-reviewed studies have shown a real effect of acupuncture is in the treatment of chronic pain.
Your brain interprets music, tones and frequencies, and if you have a good feeling or a bad feeling, it creates an emotion. Why? Those are just tones and frequencies. Why? How does it make that leap?
That is a great question. And the amount of praise I heap on the question is going to illustrate that I don't have a very good answer for that. No, I think it's a very important question, and in fact, there's a whole book written on this subject by someone who's really thought about it a lot, and it's a book called This Is Your Brain on Music, and it's by a guy named Dan Levitin. And I apologize for punting, but this is a subject in which I don't know all that much, and so I'm just going to have to turf it over to that, and if you can read a review of that book, then that'll be helpful. Okay, good. All right, good. So I apologize for not knowing the answer to that. I don't want to BS you.
Is there any chance at all that the brain is a quantum computer?
No. Well, okay, so to elaborate, there's one category of ideas that's popularized by Roger Penrose that, for instance, microtubules can somehow engage in some quantum transitions, blah, 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 that can account for some of the unpredictable properties of brains. And that particular set of ideas has very little support in experimental biology. Among other things, the quantum transitions that have been seen, I think, have been observed in vacuum, which I think you would agree our brains do not exist under. So there's a real problem with a lot of those ideas. It's an interesting idea, but there's some real problems with it.
What do we know about what's happening in the brain under general anesthesia?
Where's the person asking?
I'm back here.
Okay, all right. What's happening in the brain?
Under general anesthesia.
That's a great question. This is, in fact, a question that not very much is known about. I'll tell you the kinds of things that are known. So I told you that the brain uses 12 watts of power. And that's measured by, for instance, measuring how much glucose comes out. You measure how much glucose is in the carotid going in, and you see how much is coming out. That's the typical way of measuring it. There are other ways of doing it, too. That figure never changes. When you're playing chess, it's 12 watts. When you're sleeping, 12 watts. When you're unconscious, 12 watts. General anesthesia, 12 watts. When you're in deep, deep, deep coma, 6 watts. Okay, and so basically there's this weird phenomenon in which a lot of neural processes appear to be going on and on and on, no matter what your mental state. And because of that, it's a real puzzle why general anesthesia works. And so there used to be an idea that general anesthesia just kind of generally liquefied neuronal membranes and created some kind of non-specific effect. It's not so clear that that's true. Now there's a belief that perhaps there's some specific effect on particular neurotransmitter receptors. But I have to say, this is a very unworked out area. It's amazing that it's unworked out, right? When you consider that basically someone figured out that ether did something and it gained currency as a surgical technique. I mean, we're glad to have general anesthesia, but it's not known. It's an amazing thing that it's not known. Despite the, yeah.
You mentioned the myth of alcohol destroying brain cells. Could you comment on how that started and why you know it's not true?
Okay, so the origin of the belief probably, I'm not sure about this, but probably resides in the observation that decades of heavy drinking can lead to shrinkage of brain mass. Okay, so this is an observation that's been made. But it requires decades of drinking to do that. When people have done careful measurements counting the number of cells in people with those shrunken brains, what they found, perhaps surprisingly, is that the number of brain cells is not decreased. Now, the probable reason for this is that cells are not just little balls. They are things that have tree-like structures coming out of them called dendrites, which are their inputs. And it's likely that those dendrites retract a little bit. And so what's probably the case is that that's what's going on. The amount of drinking it takes to kill brain cells is really tremendously large, and it only occurs in a phenomenon called Wernicke-Korsakoff syndrome, which is a case in which you drink so much alcohol that that's how you get your nutrition, and then you end up with a B vitamin deficiency, and then that kills the neurons. Okay, and so now the good news, so there are several lessons from this. One is you're not off the hook with heavy drinking because, of course, shrunken brains still have reduced function. But there's good news, which is that, in fact, that brain mass has been demonstrated to recover somewhat when people stop drinking. And so there's a piece of good news here, which is that means that the damage that's induced by heavy drinking for many years is reversible. So that's the long answer. There's several people who've been madly waving their hands in the back, and I feel so bad for them. One gave up, I think. Okay, good.
Has the effect of Qigong been studied?
Qigong?
Yes.
I don't know a whole lot about Qigong, but I guess this is also having to do with the flow of Qi that it's believed to occur during acupuncture. Is that right? The same general idea.
I believe it also has to do with concentration.
Yeah. Okay, so...
And learning new disciplines. Just as, for example, in learning new steps, but much more complex than dancing, for example.
So, okay, I'll start with good things. Many of these techniques are techniques for relaxation and for focus and concentration, and those almost certainly are good for mental function in various ways that have to do with phenomena that we, to some extent, already understand, such as I said, reducing the effect of stress hormones, for instance, right? Stress induces hormone secretion that physically damages the brain, and reduction of stress hormones is good for the brain then. So that's one category of likely effects of things like Qigong. Now, there's an Eastern idea in the concept of Qi, which is that there's some substance that flows through the body, and it flows through the body along these things called meridians, and it's translated as the word energy. One thing that's been pretty well demonstrated is that there is no energy flow that occurs during this phenomenon. Now, all that means is that the word and the concept are translated poorly. Okay, it just means that it's not electromagnetic energy, and you can't see a little pointing vector that goes down the arm or what have you when you stick a needle in or whatever. So all that means is that the concept does not map to the idea of physical energy. There may be something else going on there, and I think some of the ideas are extremely interesting, but it's not clear. I think my personal feeling about that is that a lot of that stuff is basically a visualization technique to allow you to obtain the benefits of those methods, but that the actual things that are happening are probably very different from the things that you visualize. That's my feeling about it. It's a feeling. What do you want to do about time? I'm happy to take more questions. People don't seem bored, so
could you comment a little bit on where the research stands on the function, brain function relative to dream sleep, the importance of it, and what kind of physiological benefit it may have for the brain?
Yes, I'd love to. That's a great question. Okay, so let's see. So where to start? So it's generally known by many people, not just scientists, that it's discovered about 40 years ago that there's rapid eye movement sleep, and that's the time during which dreams occur. In the last few years, there's been research that suggests the possibility that dream sleep is a time during which memories are consolidated. And this appears, it's not terribly well studied, and there's some controversy attached to this research, but the general idea appears to be that changes that happen in the brain or experiences that you experience during the day get played back in some form and then are a means by which the brain can consolidate memories. And it's been speculated that, in fact, maybe wrong memories get thrown out, or experiences that are not important enough to be stored get tossed out. It appears to be a phenomenon that requires multiple days. So, for instance, it's been observed that you dream about a day's experiences, but you generally do not dream about them that evening. You generally dream about them the following evening. Okay, so this has been observed in studies of dreams. This connects up with another area of memory research that's very interesting right now, and there's growing evidence in the last few years that memory is not a thing that you write down on a hard drive. You know, there's a sort of analogy that we have, it's like storing something on a hard drive and it's there, and you know what, here's a memory and we can go, put it away someplace. It appears to be the case that memories during playback are rewritten. Okay, and so there is some sense in which it appears that the recall of the memory involves the restorage of the memory. And so the idea that people are very interested in right now is that the recall of memory plays an active role in the restorage of the memory. And what that means is that when you remember something, you're doing something that physically causes that memory to be strengthened. So I'll give you examples of how this can be important. One way in which this is important is it means that memories can drift a little bit. Okay, so if you've had an experience that you shared with another person, say with a spouse, you two perhaps experienced the same thing, and then years later, one person talks about it and says, that's not what happened. And that is probably because of the kind of drift that happens in memories. Okay, so that's, and there are other implications of this, but that's one example.
Explains Bosnia. Let's see.
Yes, I was under sniper fire. She might actually remember that way. It's entirely possible that she genuinely remembers it that way. And, you know, I certainly remember things that have not happened.
So going back to the memory thing that you just mentioned, so can you say a little bit more about how physically information is stored? So where exactly is information stored in the brain?
I can give you a speculative answer to this, and as long as you don't come back to me in 10 years and say that doesn't seem to be exactly the case. Okay, so on short time scales of, say, seconds, working memory, such as the storage of, say, a telephone number, appears to be stored in the form of a pattern of activity that perhaps continues in some kind of reverberating echo. This is the best idea for what a working memory is. Okay, so it's like there's something in your head that just maintains, 805-247-1999, 805-247, so you got that in long enough so you can get to the phone and dial. On longer time scales that are different kinds of cellular processes that kick in, on the time scale of minutes to hours, there are probably changes in the strengths of individual connections, and those connections are probably changed in response to an experience so that a particular sequence of neural firing gets strengthened, right? So A fires B, fires C, fires D. If that pathway gets strengthened, then that's a form of storage. And then on longer time scales, there are much more complicated things that happen, such that, say, perhaps a recent experience gets stored in your hippocampus, and then after this repeated recall that we were just talking about, it may get transferred into another structure, such as the cortex. And so this accounts for the fact, for instance, that you may know what the capital of California is, and you would probably respond Sacramento, but you would not necessarily be able to recall exactly where you learned that fact. And that's an example of a case in which memories get reprocessed, and you remember the fact, but you no longer remember the source. And that's a phenomenon known as source amnesia. And so there are things that happen in the processing of memories that are quite complicated, and we're not even aware of them. I think he means maybe. I'm okay with it. I mean, it's just a question of how much capacity people have. I mean, I'd say 5 minutes or so.
Is there anything to the notion that a child's brain, as they begin to grow, that there's a surge of hormones that connects the two halves of the brain together somehow or other? I've heard that.
Yeah, I've never heard that idea quite put together in that way.
Oh, okay.
Right. So we often talk about children and adolescents not being able to think straight because of the action of hormones. Right. So that's a fairly, oh gosh, he's just acting out, and it's just hormones. So, pardon me. A lot of those ideas have to do with the establishment of long-range connections, and I think you're touching on that subject. So just to give you a general picture of child and adolescent brain development, there's a tendency for the brain to mature from back to front, so that over time, the most frontal structures are the last to really hook up their connections. And it's been observed, for instance, that some of the long-distance connections in the brain have this fatty sheath that helps them conduct over long distances. That sheath is called myelin, and that myelin sheath develops quite late, often into adolescence. And now the reason this is interesting is that the prefrontal cortex is important for phenomena such as making plans for the future, executing those plans, self-control. Okay, does this sound familiar? Right. So these are okay. So it makes sense that people who are, say, youthful offenders or hot-headed in their youth then settle down later on. And that's because there are physical changes that are literally not complete until people reach their 20s. Right. And so and a lot of those are not really hormonal per se, although those developmental processes are driven by hormones, but they're not necessarily driven by hormones the way that we colloquially think of them. Right. So a lot of that stuff is just basically brain maturation.
So is there anything to this left brain, right brain stuff that we used to hear about 20 years ago?
There is, but it's mutated into something else. So the original finding is pioneering work from my alma mater, from Caltech, in which Roger Sperry and his collaborators looked at the patients of people who had their brains split down the middle, and they found that verbal abilities resided entirely in the left, in most people entirely in the left hemisphere. And when they quizzed the right hemisphere about things, they found that the right hemisphere was unable to generate speech. Okay, and so this is the seed of the idea. So roughly speaking, we think colloquially of the right hemisphere as being the seat of creativity, right? So this is a thing that we get taught about, drawing with the right side of the brain and stuff like that. That's probably not quite true because, for instance, in the absence of information, the left brain will generate language and make up explanations. And so, for instance, if you show the right half of the brain this is an experiment that's been done. If you show the right half of the brain a dirty picture, the person will giggle uncomfortably. And then you ask the person, well, why did you giggle? And the left hemisphere is the only hemisphere that can generate language, and it'll say, oh, you showed a funny picture. Oh, that was so funny, the picture. And people will confabulate reasons even though they're unaware of what's going on. And so there's this storyteller in the left half of the brain that needs to tell a story so badly that in the absence of real hard information, it'll just make up a story. Okay? And so clearly there's some creative function in the left half of the brain. It's believed that spatial reasoning appears to, in most people, sit in the right half of the brain. So there are differences between the hemispheres, but probably they're not exactly the way that they're depicted in pop culture. And besides which, the hemispheres, have this massive communication through the corpus callosum. And so basically, your entire experience is left and right halves of the brain doing this all the time, right? The fact that the left brain controls the right hand, the right brain controls the left hand, the fact that I can do this, okay, tells you that there is some kind of fast communication between the halves of my brain.
Yes, on that same subject, I had heard at one point in time that early on in infancy, the two halves don't operate flawlessly together. In fact, the child cannot reach across the center line until some point of development. Is that true?
Yes, I've been watching that. In my daughter, yes, I've been really, my wife is a physician, and so she's, ostensibly not too sentimental about these things. But I'll go like this with the baby. And she said, "What are you doing?" I said, "Well, she's not tracking across the midline." I mean, that was many months ago. So that, right.
At some point,
yes, that's right. That's right. So, and one possibility there is that there's connectivity that gets set up at the corpus callosum, right? Because there's a lot of development that happens postnatally and through about the age of 6. So the brain reaches about its full size around the age of 6.
I'm particularly interested in antidotes to dementia, and you said doing things like Sudoku aren't particularly helpful, but being highly educated is. So what I'm wondering is as you age, is it helpful to learn new things that you're not good at rather than doing the same kind of puzzles that you're already good at? Would that be?
Absolutely. So in general, the thing that people talk about when they study risk factors associated with dementia and also mental decline is that it's important to have an intellectually engaged lifestyle. And this is a catchphrase that appears in psychology literature and also in clinical literature. And the general idea is to have new experiences, to have complex hobbies, to do complicated things. And as I said, it can include things like learning a language or doing something complex. I mean, what the complex thing is can depend on your taste. But yes, coming to lectures, thinking of questions. These are real enhancing activities. So in general, I think that there are many things that one can do.
You spoke about, is it my turn? The right and left side of the brain. There is exercise called brain gym where you're supposed to cross the body, and it's supposed to help memory and all sorts of things. I'm curious if you're...
How much does that cost?
We've done it for free.
I think that you would be better off getting a pair of gym shoes.
So Sam is running out of power, and I'm going to exercise my prerogative as director. He only has 12 watts at a time, so
right.
To ask a question, actually. I'm often asked when I give lectures about QCD or string theory, and I talk about the great puzzles that face us in physics. So people ask, maybe we're just not intelligent enough to grasp it. And so I'm asked, is there any limit to human intelligence? Are there perhaps issues, and I explained that, well, that's a good question because I've been unable to teach quantum mechanics to my dogs. I think my dogs cannot learn quantum mechanics inherently, no matter what I do.
Maybe they just can't learn it to your satisfaction.
No. They've been... That's true of my students, not my dogs.
Oh.
But so, I have an answer for this, which I could try out on you, but I'd rather hear your response. Do you think, as a brain scientist, do you think there's a limitation to human brains as opposed to obvious limitations of our fellow mammalians?
So let's see. So what seems to be amazing is that even with the advent of modern technology, we seem not to have, in some sense, reached those limits, right? So the effect I pointed out of IQ scores rising several points per decade, in some ways, people who lived 100 years ago, in certain aspects of IQ tests, would score at 80 on modern IQ tests. Okay, now not the concrete parts of IQ tests. They're average. Those people 100 years ago were just as good at concrete reasoning, but they would be less good at many kinds of complex reasoning, abstract reasoning. Another example of things that people are becoming much better at is multitasking. So there are certain kinds of multiple task performance phenomena, and people who are, say, under the age of 20 get a lot of practice at these things due to things like video games. And they appear to be able to switch tasks in a very measurable way, better than say, I can. And so that's another example in which mental capacities appear to be still being improved by changes in daily experience. But let's see, so your question...
Improved or altered? I'm really asking at a conceptual basis. One obvious difference between us and all other species is what we call human intelligence.
Right.
Is there a limit to that? Are there things that we could not grasp, our brains, as constituted? Or do we have limitless powers of comprehension?
So one thing that's come up in the last few years of research is that biological evolution appears to be happening, in the case of brain evolution, faster than previously appreciated, but it's still on a time scale of thousands of years. And so in some sense, the answer to your question is that biological evolution is still a pretty slow process. Now, is your question, is there something that we can never grasp? Mm-hmm. Yes, right. Coming up with a good testable experiment to test string theory. That would be something that appears to be currently out of grasp.
Okay. No, that's not a good example. Actually,
so what's your answer?
The things you can't grasp are probably the things are not things you could identify, which is why the question is tricky. I'm sure my dogs wouldn't recognize the fact that they don't understand. They can't be taught quantum mechanics. So it's tricky. And it's really a question. The obvious biological answer is any naturally evolved apparatus is bound to be finite. It evolved for certain tasks.
Right.
And might improve at this slow pace, or we might learn to improve it. My answer is twofold. One, theoretical, that the greatest human invention of the brain, which you didn't get into very much, is language. And language sort of has an infinite capability. It's mathematics is sort of the perfected form of language, and as Chomsky has pointed out so forcefully, language sort of has this infinite capability. Your daughter will utter sentences, I predict, in the next year or two, that have never been uttered before by any human. There's this infinite capacity of language, an invention of the human mind, but in some sense, we haven't yet seen its limitations. And the other experimental fact, which I bring about basic physics, is simply, how would we know that we're not able to grasp something which we can't even grasp, the thing we can't grasp, like quantum mechanics? We would see that graduate students would take longer and longer to get educated. We would, instead of just taking 25 years before you get a PhD, it would take 30 and then 35 and then they just never get to the point where they could, and that isn't the case. So one thing that hasn't changed over 400 years, where we are probing harder and harder problems, farther and farther from our daily experience, more abstract, et cetera, is the rate, the behavior of young people is identical. At the same kind of age, they're able to get in. So we're not getting close, I think. But maybe language has infinite capability.
I think at a very abstract level of the very advanced kind of thinking that you're talking about, I think that this is entirely possible. There are some fundamental limitations that we as big naked primates have to put up with as things that we have to physically, as people, things that we have to overcome in order to be able to think rational thoughts. Our rapid decision-making processes are not rational, right? We have these shortcuts that we use to help us survive in the world, built by natural selection, acting over many thousands and in some capacities millions of years. And these capacities aren't rational. They're just there to help us survive and make replicas of us in the future. So I'll give an example. People buy lottery tickets. Okay. Now, mathematically, you know that lottery tickets are a bad idea, but it is undeniable that people buy lottery tickets and enjoy buying lottery tickets. And it appears to be the case that people gauge the probability of winning the lottery approximately in proportional frequency to how often they hear about winning the lottery versus how often they hear about losing the lottery. This is serious. This is how people estimate probabilities. They estimate them based on, what they hear, and people are very social. And so that's an example. Here's another example. I realize that these are very low-level examples that are not very illuminating for discovering secrets of the universe. But another example is, here's an example. I want you to answer this as quickly as you can. Together, a bat and a ball cost $1.10. The bat costs $1 more than the ball. How much does the ball cost? So of course David answers right away 5 cents. But the idea here is that your rapid shortcut reasoning is, 10 cents. And so obviously the answer is 5 cents, because $1.05 plus 5 cents equals $1.10, which is the quantity I told you at the beginning. But these are examples of rules of thumb that we use that are in some sense nonlinearities in how we reason about experiences that we have in the world. And so there's this lizard brain inside us, right? It's our inner lizard that is telling us all these things. And so there's this fundamental thing that we have to overcome in order to do these fancy things.
Yeah, well, that's why we go to graduate school, to overcome that.
Right.
Well, thank you very much.
Thanks for having me. That was fun. Great fun.
Sign in and refreshments.
Refreshments.